Phase changes is probably something you were exposed to in K through 12. So I'm going to leave this slide up to you. We know we can go from a solid to a liquid and a liquid to a gas. We know we can go from the gas to the liquid and from the liquid to the solid. The red arrows we see here are when we have to input energy. They're labeled endothermic, whereas the blue arrows is when energy is released. They are referred to as exothermic. What I want to focus in are the terms we need for this course. Fusion is when you have a solid and it goes to form a liquid. You may know it more as melting, and we'll talk about the melting point, the MP. There is an enthalpy associated with it, and that is the heat of fusion, delta H fusion, and it's the heat required to take 1 mole of solid to the liquid at the melting point. So that is melting. And what we also have is boiling. Boiling is referred to as vaporization, and that's when we have the liquid go to form the gas, and that takes place at the boiling point, or BP. We have associated with that an enthalpy called the heat of vaporization, and it's the heat required to convert 1 mole of liquid at the boiling point to the gas. You'll see more of this on my following slide. But both delta H of fusion and delta H of vaporization refer to intermolecular forces. When I have a delta H of fusion of ice, when I'm going from the solid to the liquid, I'm just trying to break up that lattice, okay? So it does take energy, but it doesn't take that much energy. When I'm trying to go from the liquid to the gas phase, I'm trying to separate all the molecules. And you can see that the heat of fusion of ice is much, much less than the heat of vaporization of ice because it's less energy to slide when we're breaking the lattice versus separating when we're going from the liquid to the gas phase. All of this is a prelude to what's called a heating curve. So our first slide showed you a picture with all the terminology. What we have now is what is called the heating curve, where we plot. We plot on the y-axis the temperature in degrees centigrade, and on the x-axis, we plot the heat added. Now, this has often given students trouble because normally temperature is on the x-axis, but each division in this picture corresponds to 4 kilojoules. When I have a horizontal portion on this graph, that would be the red part here and the red part here, that means constant temperature. So when something is melting or boiling, the temperature does not change. Look over at the y-axis. Notice water freezes or melts at 0, water boils or condenses at 100. Okay, so that's an important point. The length of whatever portion we have, it's the heat I have to put in to make the change because again, each division corresponds to 4 kilojoules. You see there isn't much heat put in to melt, but there's a lot more heat in order to vaporize. And the slant, well, that's going to be the specific heat that we talked about back in chapter 5, okay? So the enthalpy delta H, it measures how much heat is involved. We will be doing something we did before, calculating Q, and we'll calculate Q for each section. So essentially, you're probably jumping up and down. No, not really, but I'm joking. It's the same equation that we had back in chapter 5, and you'll run into one of 2 different types of situations. The first one says, if I have a piece of solid sodium and I have 5 grams, how much heat do I need in order to melt it? Well, think of the heating curve. We know it looks like this. And when we talk about melting, melting happens right here. We are sitting at a constant temperature. We only need to do one calculation. So many of you will say, I don't know what to do, but I'm going to put it this way. We have 5 grams of sodium, and we still turn things into moles. 1 mole of sodium is 23 grams of sodium, and what they tell us is 2.6 kilojoules are required to melt every mole of sodium. When I crunch my numbers, 0.57 kilojoules. So again, this was one calculation, and it was along the melting point portion of the heating curve. Now, what if more happens? Well, what you'll do is just add things together. On my next slide, what I have is how much heat does it take to convert 180 grams of water at 10 degrees all the way up to steam at 105. We're going to break it into 3 parts. We're going to say 10 degrees centigrade to 100 degrees centigrade. That is where we are having water be as a liquid. Then we're going to be at 100 degrees centigrade. Well, that is the boiling point, and that's where the liquid is going to form a gas. So we have one calculation, a second calculation, and a third calculation is where we're going from 100 degrees centigrade to 105 degrees centigrade. That's where we are in the gas phase. It's as simple as the sodium calculation before. We just have we have a couple more numbers. We have 180 grams of ice. We know the value for specific heat of ice is 4.18 joules per gram degree centigrade. And we know that our final temperature is 100, and we started at 10 degrees centigrade. That'll give us a numerical value of 67,716 joules. So we're doing one segment of the curve. The second segment is the boiling point, and the delta H vaporization is 2260 joules per gram. We don't have a temperature term because vaporization occurs at a constant temperature, and our value is 406,800 joules. Finally, we have to put it into the gas phase. 180 grams, it's the same all the way through, but now we use the delta H of vapor, we use the specific heat of steam. Sorry, it's hard to say it, easier to do. 1.84 joules per gram degrees Kelvin. I guess I have centigrade and Kelvin. They're both the same. They're equal in terms of size. And we have 105 as our final minus 100 degrees centigrade. I like centigrade better. And we come up with 1,657 joules. This is a very simple calculation. We come up with 476,173 joules, or 476 kilojoules, and it has a positive sign, and that refers to the heat that is absorbed. So chances are there'll be one of these on your exam. I used to always give one. I felt I wanted to see if a student understood what the heating curve was. So I've already done the math, but a heating curve will always look like this. We've got our solid, we have our liquid, we have our gas, we have our melting point, we have our boiling point. What did we have in this problem? The liquid was number 1, the boiling point was number 2, the gas was number 3. Please come to the Zoom lecture. I can take my time, draw a little bit more, but for this, I want it for the record, just so we have it.